All right, so this is a lecture for chapter 5, which is going to cover nuclear chemistry, which we'll be more familiar with by calling it like radioactivity or radioactive decay, like studying those sorts of things. We're going to notice, and we'll see this throughout the chapter, that there are a lot of interactions with um, different types of radioactivity in our daily lives. I think that it's present a lot more than we even realize. Radioactivity comes from unstable nuclei. All right. So when you have a nucleus of an atom that is not stable, it's going to try to become more stable. So when you have an unstable nuclei, changes are going to occur within it that are going to kind of cause it to change into something else. And as that change happens, particles will be emitted, and that those particles that are emitted, that's the radiation that we're going to be seeing. You'll find unstable nuclei in a lot of different elements. A lot of different elements can have isotopes that are radioactive while other isotopes are stable. Carbon and hydrogen are two elements that are on the smaller scale that have radioactive nuclei in certain isotopes. But we see a lot of the radioactive elements occur with atoms that are, or elements that have an atomic number of 20 or higher. The lower in atomic number that our elements are, the more stable they are in general, although obviously there are some exceptions to that. An unstable nucleus is going to be one where the the nuclear forces that hold our nucleus together, they they can't manage to overcome the repulsive forces of the protons that occupy the nucleus. Because remember that in your nucleus, there's just going to be protons and neutrons. All of the electrons are outside of the nucleus. So in your nucleus, you have a whole bunch of positive charges that are really close together. And when you have charges that are similar, that are near each other, that is going to cause things to repel from each other, right? They'll try to move away from each other. But what's also present in the nucleus is called the strong force. And sometimes just the particles themselves can contribute to the strong force. The neutrons that are in there can contribute to the strong force. And these like outside forces are there are strong enough in stable atoms to kind of keep that nucleus as whole, keep it together. When those forces, those nuclear forces aren't strong enough, then the repulsion from the protons, it kind of wins that battle, and that's when you have the radioactive decay happen, and the nucleus of your atom like tries to transition into something else that's a little more stable. Our main forms of radiation are going to be these four things. Okay, we're going to have alpha particles that have this symbol. We're going to have beta particles that have this symbol, and we're going to have positrons, which have this symbol. And then we'll also have this pure high energy called gamma rays. Your gamma rays aren't going to exist as particles. Like each of these three things exist as separate particles that you can sort of um, take account of in a nuclear reaction. But your gamma rays are less like particles. They're more just pure energy that's going to exist within these radioactive decay processes. This term, radioisotope, is the name that's given to any isotope of an element that is unstable and that is going to go through a decay process that has it emit radiation. Okay. Um, you can have isotopes of elements that are stable and that will not decay. You can have isotopes of elements, multiple isotopes of elements that are unstable and will decay. Okay. Um, it's a matter of that ratio of protons to neutrons that are in the nucleus and whether or not the nucleus is able to hold itself together or whether it's going to be more prone to like come apart. You're going to see that for our radioisotopes, we're going to kind of note them the same way that we were looking at isotopes in our previous chapter. So the mass number will be in the upper left corner. The atomic number, which will be our number of protons, will be in the bottom left. And then the symbol of the element will be next to that. All right. And we'll refer to the different isotopes by their mass numbers. So this one would be called iodine 131, for example. These are just some examples of stable isotopes versus radioactive isotopes. And you can see that something like magnesium, which has a stable isotope, also has multiple radioactive isotopes. The same is true for iodine. Then we have something like uranium, which has no stable isotopes. All of the isotopes of uranium will undergo some type of radioactive decay. All right, so back to our different types of radiation. There are some other symbols that you can use to represent each type of radiation. For your alpha particles, you have your little symbol, which looks kind of like an A, which is helpful to represent your alpha particles. But you're also going to see that alpha particles, what they're made of, is going to be exactly identical to what's inside of a helium nucleus. That means that alpha particles contain 2 protons and 2 neutrons. So a lot of times they're written like this, which would be the representation of a helium nucleus. All right, so you can see the symbol for alpha particle, or you can see this 4,2 He, and they mean the same thing. They both mean alpha particles. Then we have our beta particles, which we get our like scripty B symbol to represent our beta particles. And our beta particles are going to exist as high energy electrons that are going to be emitted from our nucleus as the radioactive decay occurs. Another symbol for our beta particles is going to be a 0 for the mass number and a -1 where the atomic number would be, and a lowercase e where the chemical symbol would be. So if you see this symbol, it's representing a beta particle or a high energy electron. Okay. Then there are positrons. Positrons, and we'll talk about this more when we go through each type of radiation, but positrons are going to be the exact opposite of beta particles. Okay, they're like the anti-particle of an electron. And so the way that we're going to write their symbols will be the exact opposite of our beta particles. So for our positrons, we'll use the same like script EB, but we'll put a little positive sign up there. And for our other version of our notation, we'll put a 0 in the top left and a +1 in the bottom left, and then a lowercase e. So this would represent a positron. And then our pure energy or our gamma rays is going to get our symbol here, or we can write the 00 with that same symbol there, and that would represent gamma rays. All right, so this is just a breakdown of those different types of particles. These are all the ones that we've mentioned so far: alpha, beta, positron, and gamma. Their symbols. You can see the mass number for each one. The alpha particle is the only one with a mass number. Our beta particles, positrons, and gamma rays don't have any. And you can see the relative charge on each one. So the charge on the alpha particle is +2 because it's representing the helium nucleus. And the helium nucleus doesn't include any electrons, so it's going to have a +2 charge. The beta particle would have a -1 charge. The positron would have a +1 charge. And our gamma rays have no charge. The other types of material that you'll see in these radioactive decay equations, reactions, are protons and neutrons. Okay, and there's a couple of different ways that we can represent protons and neutrons in a nuclear equation. So we just want to make sure that we look at that. For our proton here, we can represent it as the hydrogen with a 1 on top and a 1 on the bottom. This is the nucleus of a hydrogen atom. So it's going to have a +1 charge. We can also represent it with a symbol, lowercase p. Sometimes people put a lowercase p with a little plus sign up here. Those can all represent a proton. Remember, protons will have a mass number of 1 because there'll be one proton, but nothing else. No neutrons or anything like that. And then to represent a neutron, very similarly, we'll put a 1 up here where the mass number is, but we'll put a 0 in the bottom left because there are no protons. And then use a lowercase n. Or we can just use the lowercase n to represent the same thing. But keep in mind that the mass number for your neutrons is still going to be the number 1 because it has 1 neutron in it and 0 protons. Okay, so the charge on your neutron is going to be 0 because there is nothing in it that gives it any charge. All right, so those are the different types of radiation. And we'll talk through the decay processes of each one in a minute. But we're going to want to look at the biological effects of radiation on the human body. When you have radioactive particles interacting with different molecules, different atoms that it encounters, what ends up happening is that the radioactive particles are going to end up knocking electrons out of sync. Okay, they'll knock them away from the neutral molecules. And instead of these neutral molecules, we're going to end up with very unstable ions that form in place of those previously very stable, very neutral molecules. And these unstable ions end up going into chemical reactions that we don't want to happen, right? They're undesirable chemical reactions. We don't want them taking place. And a lot of the effects of that are things like cell damage. You have things like damage to reproductive organs, damage to any of the cells in your body. Long-term effects of radiation is cancer is one of the effects of that, right? Because that's going to have that mutated cell that really actively keeps dividing and replicating itself. But that mutated cell, one potential cause of it comes from something like this, where you have this unstable ion entering into these reactions that you don't want happening inside your body. So we're going to look at different types of radiation that are able to penetrate different depths of your body, and then see how the ionizing power of each of those different types of radiations, what that looks like. There's two main, I guess, comparison points when you're looking at radioactivity and, the types of radioactive particles that you're working with, ionizing power and penetrating power. The ionizing power of something is going to be its ability to actually ionize other molecules and other atoms around it. And that term, when we say that it's ionizing something, that's like from the previous slide when we said that it pushes those electrons away and it causes those positively charged molecules. That's an example of ionization. When you take something that was neutral and it ends up having a charge. Okay. And then we have the penetrating power, which is the particle's ability to actually move through different layers of like protection, whether it's like clothing on your body or your skin cells or whatever. But how good a particular particle is at penetrating matter. Okay. So you see some examples here. These are our alpha particles, beta particles, gamma particles, alpha particles, beta, and gamma. And you can see that in both examples, the alpha particles, they don't have a very good penetrating power, right? So in this case, a very, very thin piece of lead is able to block the alpha particles from progressing. If you look at the diagram here where they're trying to like relate what you're seeing to human skin and human tissue, you see that your skin is a barrier that is thick enough to block alpha particles from entering. And that's good because even though alpha particles have a very low penetrating power, they have an extremely high ionizing power. So they'd be very dangerous to enter the body. Our beta particles are going to be in the middle. They can penetrate further than alpha particles, but they still are pretty easily blocked by thin shielding. In terms of your body, they would get into some tissue, but not super far. And then we have our gamma particles, which are able to pass through many different types of shielding. Your gamma particles would be able to go right past skin, tissue, bones, into organs. um, when you know that you're going to be working with any type of radiation, you are going to be wanting to provide yourself with some type of protection from that radiation. And the type of protection that you're going to require is going to depend on the type of radioactive particles that you know you'll be working with. So if you're working with alpha particles, you don't need very much in terms of shielding. Just having some clothing, like paper is thick enough rather to block alpha particles. So if you're just wearing your most basic covering, then you'd be able to block alpha particles from interacting with any of your skin or anything like that. For beta particles, you need a little more protection, but you still can don't have to do anything like super dramatic. Like you can have a kind of a thick lab coat and some gloves, and that would be enough to block your beta particles. For gamma rays, this is when you're going to need super dense shielding. So for gamma rays, you'd need something like lead, something like really thick concrete in order to block gamma rays. Okay. But the best thing that you can do if you are working in an environment where you have radioactive material nearby is to just try to spend as much time away from the main source of the material as possible, right? Because distance is your best protection from a radioactive source. This is just an example of the depth that the different types of radiation is able to travel, the types of shielding that works best for each type. And we want to be able to look at something like this and then figure out what type of radiation what type of radiation protection each of these would work for, like the different types of radiation. I said that really weird, but we want to know, like, heavy clothing. Could you use that for alpha protection, beta protection, or gamma protection? Um, and so something like heavy clothing would be okay to use for alpha particles as well as beta particles, right? If we had paper as our shielding, then the only type of radiation that we could block would be our alpha particles. For lead, this would kind of depend on the thickness. Probably should put some kind of descriptive modifier in there. If the lead is thick enough, it would be able to stop alpha, beta, or gamma particles. If it's very, very thick, it can stop gamma particles, but it can definitely stop alpha and beta particles. Very thick concrete would also be able to stop alpha and beta particles as well as gamma particles if it is thick enough. All right. But for lead in your concrete, while those will very easily block alpha and beta particles, the effectiveness of blocking something like a gamma ray is going to depend on how thick the lead or how thick the concrete is. So let's look at some nuclear reactions. These are the way that we're going to represent the decay processes that are happening. And what we're going to see in each of these nuclear reactions that we look at is that we're going to have our reactants on the left side, and we're going to have our products on the right side. And we're going to see that our reactants, which we can also call our parent isotope, we can look at the mass number and the atomic number of our parent isotope. And when we compare it to the daughter isotope and the radioactive particle that's emitted, we'll see that the mass number of the products adds up to the mass number of our reactant. The atomic number of our products adds up to the atomic number of our reactant. Okay, and that's going to be true for every one of our balanced nuclear equations. All right. So the process that of taking something that is radioactive and then having it sort of turn into an isotope of a different element and release a radioactive particle. That process is called radioactive decay. That's the unstable nucleus literally breaking down because it is not stable. So it's turning into something else. And so we're going to see unstable isotopes have something in their nucleus change. Okay. And when that change occurs, they're going to be left with a different number of protons and or neutrons in the nucleus, which means that potentially the identity of the element could change. And we're going to see a radioactive particle release. All right, so we're going to look here. We have a couple of examples to look at for each type of radiation. This is asking us to complete the following nuclear equation for the alpha decay of Rn-220. Oops, there. So it's telling us that we have alpha decay of Rn-220. So when you are looking at a nuclear equation, you start by writing your reactants on the left side of your equation. Okay. And then you can write your arrow. And sometimes it's helpful to indicate the type of decay like over the arrow so that you can kind of remind yourself. So this is going to be alpha decay. You have to know the particle that goes along with alpha decay for the next part, right? So if it's alpha decay, that means that your nucleus is going to release an alpha particle. So remember that your alpha particle looks like this, okay? So this is our alpha particle, okay? This is going to be our reactant. Or another name for the reactant is going to be the parent isotope. Okay. And then the reactant is going to it's going to emit or it's going to release an alpha particle. And then what's inside of the nucleus is going to change. And so this is what we are going to try to figure out. What is the product that forms here? So let's take our Rn-220 and let's rewrite it in the same format we have our helium nucleus written in our alpha particle. So instead of writing it in as Rn-220, we'll write the Rn, we'll write the 220 up here, and then we'll look up the atomic number for our Rn, and we see that it is 86. Okay, so now what we know is that whatever's on the product side, the top numbers have to add up to 220, and the bottom numbers have to add up to 86. Okay, so we can take our 86 and we can subtract 2. And now we know that our atomic number for our daughter isotope is going to be 84. And we can take 220 and we can subtract 4. And we're going to get 216 for the mass number of that isotope. To figure out the symbol, we're going to look back at our periodic table and we're going to find, number 84, which is polonium. And this is going to be our daughter isotope. Okay, so that's how your different nuclear equations are going to work. Now there's going to be 3 main types of nuclear equations that we're going to look at next that describe the 3 main types of radioactive decay. Every one of them is going to have, we're going to go through the same process for them. We're going to look at what we start with, and we're going to look at what we end with, and the mass numbers have to equal each other on both sides, and the atomic numbers have to equal each other on both sides. All right. So let's look at alpha decay first. The example that we just looked at was an example of alpha decay. Um, our alpha decay is going to occur when you have an unstable nucleus and it's trying to become stable. And so it's going to emit or release an alpha particle, which is what this is. And the nucleus that it leaves behind is going to be a little more stable than what it started with. Okay. So you see the equation represented here. You start with uranium 238. And when we go to our product side, we know that we're going to be emitting an alpha particle. So if I have a mass number of 4, and I know that it has to add up to 238, my new mass number has to be 234. I know that if I start with a mass number of 92 and my alpha particle has 2 protons, that my daughter isotope has to have 90 protons. Okay, and that's how I'm going to figure out the identity of my daughter isotope. All right, so this is just a summary of what we talked about with our alpha decay. It's going to occur when an unstable nucleus emits an alpha particle, which is composed of 2 protons and 2 neutrons. In the process of alpha decay, the number of protons is going to change, which will change the identity of the element. And that's why you see whatever element you start with and your reactant side is going to be different from the element that you end with on your product side. So let's look at a couple of examples. First, the nuclear equation for alpha emission of americium 241. Okay, so we're going to write AM-241, and then we're going to write alpha decay over the arrow, just like before. And then we're going to set this up in terms of symbols. Okay. The americium is number 95 on your periodic table. So when you set it up, it's going to be your AM 95 for your atomic number, 241 for your mass number. And then we know that it's undergoing alpha decay. So it's going to emit an alpha particle. I like putting the particles, the decay particles first, because then I just use them for my math that I do to figure out the daughter isotope. So I know that I'm starting out with 241. I've got a mass number of 4 on my product side already. Use my calculator to make sure I don't mess up this very simple math. So I know that the mass number of my daughter isotope has to be 237. I start out with an atomic number of 95. I know that my atomic number for the helium nucleus is 2. So that means I'm going to have 93 protons left over for my daughter nucleus. And then I'm going to look on my periodic table for atomic number 93, and that is going to be neptunium, which is NP. Okay, so that's going to be my complete nuclear equation. Try this one next. And again, for all of these videos, when you get to a question like this one, just like pause it and try it on your own, and then watch the solution for it. Okay. So atomic number 84 for that one. We know that it's going to have alpha decay. And so we're going to look at the 210. We're going to subtract 4 from it, and we'll have 206 left. We have 84. We'll subtract 2 from it. and we have 82 left. And we look up the element number 82, and that's going to be Pb, which is lead. All right, let's look at beta decay next. So like alpha decay is when you get rid of an alpha particle from the nucleus, right? So beta decay is when you're going to be getting rid of a beta particle or a high energy electron from the nucleus. But how does this happen? Because if you think about what's inside of a nucleus, there are no electrons inside of a nucleus. So something else has to happen if you're going to be emitting a beta particle. What ends up happening is that one of your neutrons that are inside of this nucleus, it decides that it wants to become a proton. And for a nucleus, which is neutral, a nucleus for a neutron, which is neutral, to become a proton, which is positive, that means that it has to get rid of its negative charge, we'll say. Okay. For a neutron to become something that's positive, negative charge has to be expelled to leave that new particle with a positive charge. And so that negativity that gets released from your nucleus, that's what we're calling this beta particle. Okay. So you'll watch what happens if you look at the numbers down here. You start off with an atomic number of 14, and it's carbon. So you know that there are 6 protons in it, and there are 8 neutrons, right? 6 plus 8 equals 14. But what happens is one of these neutrons turns into a proton. So now on your product side, the number of your protons goes up. It goes up from 6 to 7. Okay. So now you have 7 protons and you have 7 neutrons. So your number of neutrons went down by 1 and your number of protons went up by 1. But you'll notice that your mass number doesn't change because the mass number is your neutrons plus your protons. So you still have 14 things that are inside of your nucleus. It's just that the identity of one of them changed from neutron to proton. And then the negative charge that gets released when that transition happens is released as a beta particle. What you should also notice about the nuclear reaction for beta decay is that you have a positive 7 plus a negative 1. And when you add those together, you get 6. Okay. In beta decay, you're going to notice that on your product side, your atomic number will always increase by 1 for your daughter isotope. Okay. And that's because you're taking that neutron and you're turning it into a proton. Things about beta decay that are important to know. It's the decay that happens when an unstable nucleus emits an electron. It's also 10 times more penetrating than alpha decay, so it gets further through shielding, which we've already noticed. But it only has about half of the ionizing ability of alpha decay because the beta particles are smaller. So they're not going to be able to ionize to the same degree as your alpha particles. Okay, and you're going to notice that when your atom loses a beta particle, its atomic number always increases by 1, but its mass number stays the same because we have a neutron that turns into a proton. So we're going to look at 2 examples. We're going to look at this example, the nuclear equation for the decay of 42 potassium. And we're going to look at this example, which is write the balanced nuclear equation for the beta decay of cobalt 60. Okay, but I'm going to do those back to back. So I just want you to see both of the questions that we're going to do. So we're going to do that one. And then we're going to do this one. All right. We'll make this one example A and this one example B. So for example A, we're going to start off by writing out our isotope notation for the potassium isotope. So we've got 42 Our atomic number is going to be 19 because it's potassium. And then we write our symbol. We know that it's beta decay. And so the first thing that we can write is that beta particle, which is a 0 and a -1 and a lowercase e. So for our daughter isotope, when we look at the top, we have 42 and we have a 0. So that means our mass number stays 42. Here we have a 19 and here we have a -1. So you have to ask yourself, what can I add to -1 to give me 19? Okay, and again, you'll see if you ask yourself that question, that your atomic number is going to increase by 1 on your product side. 20 plus -1, 19. And when you look up number 20 on your periodic table, it's going to be calcium. So let's look at the same process for the cobalt 60 in the second question. Cobalt is atomic number 27. We know that it's undergoing beta decay, so we're going to have a beta particle here. So again, for our mass number, we see, all right, 60, 0, going to stay 60. We have 27 and a -1, so our atomic number is going to go up to 28. 28 plus -1, 27. And 28 on our periodic table is nickel. All right. The last decay process that we want to take a look at is the positron emission. Which again, it's going to it's the opposite of your beta particles. Like positrons and beta particles are going to be opposites. So what happens when you have positron emission? You have a proton that wants to become a neutron. So instead of a neutron becoming a proton, we have a proton that wants to become a neutron. The only way that a proton can become a neutron is if it gets rid of its positive charge. And so what you're seeing here is the representation of the positive charge that's being emitted. And this is what we call a positron particle. All right. So if we look at an example here, we have manganese 49, which has an atomic number of 25. And when it undergoes positron emission, its atomic number is going to decrease by 1 because one of its protons has turned into a neutron and it's getting rid of the positive charge. Okay. Our atomic number doesn't change because we still have the same number of protons plus neutrons in our nucleus, right? Because one of our protons has just changed into a neutron. So our proton number went down by 1, but our neutron number went up by 1. Again, the positron, which we can give this symbol here, it is the antiparticle of the electron, even more so than the proton is, because where protons and electrons have opposite charges, the size of protons is still significantly larger than the size of electrons. But with your positrons, these are exact opposites. Like the positron even has the exact same mass of an electron. It just has an opposite charge. Okay. And so we've talked about these other parts already, but these are just some other examples where you can see that your starting material, and as it undergoes positron emission, its atomic number decreases by 1 and it emits that positron particle. I like writing it down numerically a little bit better because then it's easier to see the numbers work out, but it can be represented like this where you just have the particle notation written. All right. For this one, I don't want beta decay. I want to do positron emission. Let me pause and fix that real quick. All right, got that fixed. So we're going to write the balanced nuclear equation for the positron emission of xenon 110. right? And so we can start by writing out our isotope notation for it. Xenon is number 54 on our periodic table. We know that it's undergoing positron emission, and so we're going to put a 0 and a +1 with a lowercase e. And now when we're looking at the daughter isotope that forms, we like, all right, we start with 110. We have a 0 here. So my mass number is going to stay 110. I've got 54 here. I've got a +1 here. So my new atomic number is going to be 53. And that is going to be iodine. And let's look at one more example of the positron emission. And that's going to be for cadmium 97. Okay, so we write down our CD 97, and then we gotta find our cadmium. Number 48 on your periodic table. Okay, and then we can write our positron particle. And then we're gonna compare our mass numbers. This is gonna stay 97. And our atomic number is gonna decrease by 1 to 47. So that 47 plus 1 is 48. And number 47 on your periodic table is going to be silver. All right. Those are the three main types of radioactive decays that you'll have to write equations for. We're going to see other types of equations, but those are the three decay processes that you'll really have to write equations for. Something like gamma radiation, which is present in almost all radioactive decay processes, is it's got zeros for its mass number and its atomic number, so it's not going to have an impact on the nuclear equation itself. It's just representing the significant amount of energy that's being released during that process. What else? What we also know about gamma radiation is that it's extremely high energy. It's going to be the least ionizing radiation, but it is the most penetrating. That has a lot to do with its size. It's real small, so it's able to pass through a lot of material that your bigger radioactive particles cannot. So we want to take a second to do each of these examples. We're going to write a nuclear equation for the indicated decay of each of the following. All right, I'm going to, again, I would suggest really good idea to pause this right here and try it on your own. I'll pause the recording real quick while I write this down. All right, so let's look at each of these examples. We're going to start each one by rewriting our symbol so that it's in like the proper equation format. Uranium 234, atomic number 92. It's going to undergo alpha decay, which means that our radioactive particle is going to be an alpha particle. And to figure out what's left over for our daughter isotope, we'll do 234 minus 4 and 92 minus 2. And then we'll look up number 90 on the periodic table, and that is going to be thorium. Okay. For our next one, lead 214. On our periodic table, lead is number 82. This is going to be beta decay. So our symbol is going to be a 0 and a -1. We know that because we have a 0 here, that our mass number is not going to change. And because we have a -1 here, our atomic number is going to increase by 1. Okay, you can always verify that back for yourself. 83 plus -1, 82. And we find 83 on the periodic table, and it's going to be bismuth. Positron emission of nitrogen 13. Remember that our positron particle is the anti-particle of the electron, so it's going to be exact opposite. Because we have a 0 here, we know that our mass number doesn't change. And because we have a +1 here, we know that our atomic number goes down to 6. So 6 plus 1 is 7. This is going to be carbon. All right, and we have actinium-227. That is atomic number 89. This is also going to be beta decay, so we have a beta particle there. So our mass number is going to stay 227, and our atomic number is going to increase by 1 to 90. And that is going to be thorium. And then we have thorium-230 undergoing alpha decay. So we put a 230 up here. Thorium's number 90 on your periodic table. You notice like both of these are thorium, but they have different mass numbers because they have different numbers of neutrons in them. So this time we're looking at alpha decay. So we know that it's going to be giving up an alpha particle. That means that its daughter nucleus is going to have 230 minus 4 is 226 as its mass number. And its atomic number is going to be 90 minus 2, which is 88, which gives us radium. And then we have thallium-207. So for that, we're going to have a 207, and then thallium is number 81. It's beta decay, so we have a beta particle there. That means that our mass number is not going to change. It's going to stay 207, and our atomic number is going to increase by 1 to 82, which gives us lead. And then for our last one, we have oxygen 15. This is positron emission, so we're going to have a positron particle. That means that our mass number, again, we have a 0 here, so our mass number is not going to change. We have a +1 here, so our atomic number is going to be 7. 7 plus 1 is 8. Okay. Those are all of our examples of our different types of nuclear equations. So let's look back at the slides. There's a little summary of those different types of radiation that we have. This is just showing us the type of radiation, the type of radioactive particle, and the changes that happen inside of the nucleus. Okay. So the only type of radiation that is not going to result in a change in the nucleus of mass number or atomic number is gamma radiation. Every other type of radiation is going to result in a change within the nucleus itself. All right. Another part of radioactivity and nuclear chemistry that we can look at is how we can create radioactive isotopes. So looking at like natural radioactive decay is not the only it's not the only way to see radioactivity or to end up with a radioactive isotope. you can actually produce radioactive isotopes through a process called bombardment. Okay. Um, bombardment is when you take a smaller particle and you hit it at very high speed into something that's stable. And the result of that is going to be a larger, more unstable nucleus. And remember that unstable nuclei are radioactive. Okay. This process where you take one element and you turn it into something else using bombardment is called transmutation. Okay. Another result of a bombardment process is frequently neutrons, okay, other types of particles. We can write the process of bombardment as a nuclear equation the exact same way that we have just done for the other nuclear equations that we have looked at. You're just going to look at what's being described in the specific process that you're working with. Okay, like a lot of these look very wordy, but you just have to write down the exact information that's given and then find the missing piece of information the same way that we have already done with our radioactive decay processes. Okay. So you have the problem here. I'm going to read it out loud and like write down the information as I go so you can just see how we should be recording it and then like finding the missing information. So it says write the balanced nuclear equation for the bombardment of nickel 58. So we have nickel 58 and we're bombarding it with a proton. And it's going to produce a radioactive isotope. So it's going to produce, this is going to be our mystery particle here, our radioactive isotope. And it's going to produce an alpha particle. So that's the information that our question has just given us. And we can fill in a lot of these things already with actual isotope notations. They tell us the notation, they remind us in the question of the notation of a proton, which is 11H. We know what an alpha particle is. It's 42He. We know how to write the symbol for nickel. Just have to find the atomic number is 28 for that. So we're going to have Ni with a 58 up here and a 28 in the lower left. And now the only thing that we have to do is find this missing radioactive particle to complete the equation. And we're still working with that same theory from earlier, like whatever's on the reactant side has to add up to whatever's on the product side. So if we look at what's in our mass number spots on our reactant side, 58 plus 1, that's 59 total. If we look at the bottom parts, it's 28 and 1, that's 29 total. So now when I come over here to find my missing particle, I know that my mass number has to add up to 59. I already have 4 over here. So my missing mass number must be 55. It's 55 plus 4 is 59. For my atomic number, it has to add up to 29. This is 2. So my missing atomic number has to be 27. And then I look on my periodic table to find the atomic number for 27, and I see that it is cobalt. And that's going to be my complete balanced equation for that bombardment process. So it always is going to look a lot worse than it actually is to solve it. Okay. Let's put up the next example. You can try this one on your own real quick. And then we can solve it together. For this one, it's nice so because they wrote out the incomplete equation for us. They're not asking us to like decipher the terms that they're given. So I'll leave a blank there for our isotope of interest. Okay, but we're going to still go through and do the same thing here. Over here, this time we're taking some technetium and we're bombarding it with a neutron. So our overall atomic number is going to be 43. Our overall mass number is going to be 99. Now, when we look on our product side, say, all right, it has to add up to 43. This is a 2. So my atomic number must be 41. This is 99. My helium is a 4. So my mass number must be 95. And then I look up number 41 on the periodic table, and it's going to be niobium. All right. All right, let's look at, share my screen again. We're going to look at how we measure some radiation. Our radiation measurements are going to be important when we're ever in the same vicinity as anything that's radioactive, because you're going to want to know exactly how much radiation you're being exposed to. There's different ways to measure this. Most every type of radiation detector is going to have something in it that's going to be able to detect the ionized particles that are a product of radioactivity. So something like a Geiger counter, which is a really common type of detection for radioactivity, is going to use ions that are created by radiation that will create an electrical current that will feed into the detector. And it's going to kind of emit that crackling sound that I think everyone's familiar with when you think of detecting radioactivity. The more sound it makes, the more radioactive material is present. The quieter it is, the less radioactive material is present. When you're measuring radioactivity or when you're measuring radiation, there are different units that you can use for measuring your radiation. You have the more common unit of a Curie, and then the standard unit of a becquerel. Radiation is measured in terms of disintegrations per second. Okay, disintegrations per second. 1 becquerel, which is the SI unit for radioactive decay, is going to be 1 disintegration per second. So every becquerel is going to represent 1 disintegration per second. The Curie, which is more like one of the older units, the same way that, or I guess just like one of the less standard units now, because everything tries to be standardized with our units now, just like with the SI system that we've used previously. But the Curie is an older unit that I think people still hold on to a little bit because Marie Curie was such an important person in radioactivity study in general. 1 Curie is going to be equal to about 3.7 times 10 to the positive 10 disintegrations per second. All right. What it measures is the disintegrations that occur in 1 second for every 1 gram of radium, which is the specific type of material that Marie Curie worked very closely with for a long period of time. But you can see how this value, 3.7 times 10 to the positive 10 disintegrations per second, it seems a little more, it's not random because there's a reason for it, but it seems more random than the becquerel, which is 1 disintegration per second. So the becquerel is just, it's a way to keep your radiation units a little more standardized. We're also able to measure the rad values and REM values of radiation. Your rad values are going to be the radiation absorbed dose. So that's going to be how much radiation is actually absorbed in body tissues, things like that. The REM value of measurement is going to focus in more on the biological effect of radiation. So the difference between rad and REM is that you might absorb radiation that potentially doesn't have a harmful effect on you, but you're still absorbing it in a higher quantity that seems healthy, the REM measurement is going to give you an idea of exactly how harmful that radiation is going to be for you. Okay. So this kind of measures quantity, and this is going to measure the effect. All right. The REM stands for radiation equivalent in humans. You're going to see the difference in the, I guess, like the type of damage different particles can do. Okay. Alpha particles don't really penetrate the skin, but if they enter the body, extensive damage is going to occur. It's not very likely that they're going to enter the skin, though. High energy radiation causes more damage than alpha particles because it's able to travel into tissue. Gamma rays are very damaging because they can travel through your body tissue, through your organs. Okay. So things are going to have different factors just depending on how much damage they could do when they're interacting with, your organs, your tissues, and things like that. To calculate a REM value for something, you're going to take your absorbed dose, which is your RAD, and you're going to multiply it by a particular factor, and that factor is going to be linked to how damaging that radiation is going to be. Okay. So you see for things like alpha particles, the factor is super high because if you do happen to absorb alpha particles, the effect on your body tissue and your organs is catastrophic. So if you're comparing alpha particle damage to gamma radiation damage, if you absorb the same quantity of both types of radiation, and they both have access to like your internal organs or your tissues, the damage that alpha particles can do would be way more significant than the damage that the gamma radiation could do. So this is just a list of different types of equalities for your radiation measurements. You want to be familiar with using these. You don't need to necessarily have them memorized, but you want to be comfortable in using the information to convert between different types of unit systems, just like we've been doing all semester. So you see that for measuring radioactivity in general, you can have the unit of the Curie or you can have the unit of the Becquerel. Both are units that measure activity. The relationship here is going to be that every 1 Curie equals 3.7 times 10 to the positive 10 becquerels. So if we had a radiation value that was already in units of Curie, we could convert them into becquerels or vice versa. Okay. For the absorbed dose, which is our RAD unit, there's another unit that's associated with absorbed dose of radiation, which is called the gray. The equality here, every 1 gray is going to be equal to 100 rads. Okay, so again, if you were given an absorbed dose in terms of rads, you would be able to convert it into gray or vice versa. And then your biological damage, which is your REM unit, another unit to represent the biological damage is the sievert. And the equality here, every 1 sievert will be 100 REM. Right. So what you do want to be able to do and what you want to be comfortable with is using these conversions. You want to be able to relate them to each other. Okay. Move back and forth between those units. You can measure radiation damage the different ways that we've talked about before. What I mean by that is like with the detectors, we can measure like, how much radiation is being absorbed at a given time. But understand that all radiation, I guess, is not going to be necessarily harmful radiation. You have things like Salmonella, Listeria, E. coli, things that are, bacteria that can pass along in food that you're gonna purchase, especially when you're thinking about the bulk way that we move and we store food when we're, going into grocery stores, going into fast food places, to get our food. So there are doses of radiation that are acceptable in terms of FDA levels, that you're allowed to expose different foods to treat them. That you treat your foods with those radiation, with that particular amount of radiation, and it can kill some of those bacteria that would be a lot more harmful than the small levels of radiation that you are going to be exposed to through that process. So when you have food passing through different types of areas in the processing plants, you might have gamma radiation pass through the food, and it would then kill that bacteria that would otherwise, stay there in stasis until you cook and eat the food. So there's sort of like a pros and cons of this, right? Because people be like, well, I don't really want to be eating food that's exposed to any type of radiation. But on the other hand, you don't want to be eating food that has that kind of bacteria that's still present in it. Okay, so we work with less harmful degrees of radiation to help limit the amount of bacteria that we're exposed to. Another use of radiation for food is helping shelf life. Okay, so if you ever see a symbol like this one on any of the produce that you're purchasing, it's because a small amount of radiation was used on the produce to kind of increase its shelf life, so that when they're harvested and they're ripe, they can be eaten for a longer period of time. The next thing we want to just look at real quick is some of the tools that we use to measure radiation exposure. This becomes particularly important when you're working in a lab or working anywhere that there is radiation present. There are things called dosimeters. This is an example of one that can measure different types of radiation particles. Dosimeters are going to work like there's different ways that different dosimeters work, but the overall process is really similar to what we've already seen previously. You're going to have something in the dosimeter itself that is looking to detect the ionized particles that are present when exposed to different types of radiation. And a dosimeter might flash, it might light up and like make flashes of light if certain levels of ionized particles are present. You might have something that emits some kind of sound. There's different, types of detectors or different types of ways that the dosimeters are showing that you're at, unhealthy exposure levels. But you can wear these and kind of monitor what's happening. There are different sources of radiation. We have our natural radiation, very small doses of radiation present. There's radiation that's present from things like power plants, even things like TV or just air travel. Just small amounts of radiation that are present. There are higher doses of radiation present in things in medical uses because you're using this radioactive material in a very specific way to try to get these very specific results or images to look at. But the time that you're exposed to that type of radiation is so short that it's not like a long-term health concern. Like we said, this is kind of like a repeat of that last slide. There's a lot of naturally occurring radiation almost everywhere that we exist. It's in our environment. It's in the buildings that we live and work in. It's in the food that we're eating. There are specific doses of radiation that will be lethal to different populations. If you remember back to the LD50 value that we previously talked about, that LD50 describes the dosage that's required for 50% of the population to die. Okay. the lethal dose for 1/2 of the population. So you could see that the LD50 values for different types of species are extremely different. Okay. But the larger the dose of radiation that you receive at one time, the bigger the impact it's going to have on your body. So if you have a large amount of radiation that's being sort of absorbed over a longer period of time, there are definitely like health effects that will happen, things like sickness or cancer. But when you're exposed to a large amount of radiation at one time, there can be like an immediate catastrophic effect on your body. Um, the next section talks about half-lives of radioisotopes and how you go through determining the age of some things or how much of a particular isotope is left after a certain amount of time passes. To talk about half-lives, we really need to understand what a half-life is. A half-life is going to be the amount of time that it takes for 50% of the radioactive material that was initially present to decay. All right. So whatever value of radioactive material you start with, the amount of time it takes for 50% of that to decay. That's going to be our half-life. So what we're looking at here, we're starting with iodine 131, and we're starting with 20 milligrams of it. Okay. And so we're going to track the amount of time it takes to get from 20 milligrams to 10 milligrams. So if we see that 8 days has passed to go from 20 milligrams to 10 milligrams, then we know that 8 days is the half-life for that particular isotope, because it's the amount of time that it took for 50% of our original amount to decay. All right. And then if we take now our first half-life has passed and we have 10 milligrams of our isotope left. And so now we're going to track the time that it takes for 50% of what we have left to decay. So our 10 milligrams is going to decay into 5 milligrams. And when we look at how much time has passed, another 8 days has gone by. So now the 16 days is our total. Okay, so it was 8, and now we have 8 more, which is 16. And now what shouldn't be surprising is that after another 8 days, when we're up to 24 days total, our 5 milligrams is going to turn into 2.5 milligrams. Okay, so at every half-life that passes, 50% of what we're left with is going to decrease by 50% again. Right? You can make a decay curve out of this that shows the correlation between the amount of material you have and the time that's passed. When 0 time has passed, that's when you have all of your material. After 1 half-life, you'll have exactly half of that material left. At 2 half-lives, you'll have half of whatever remained left. So it goes from 10 to 5. Then at the 3rd half-life, it goes from 5 to 2.5, and it continues on that way. These are some common half-lives of common radioisotopes. There are naturally occurring isotopes, which you see have very long half-lives in general. And then there are medical radioisotopes. And you're going to notice that the medical radioisotopes have half-lives that are extremely short. And that's because when you are using a medical radioisotope, you want that isotope to decay down to nothing as fast as possible so that it's not in the body any longer than it has to be. Okay. So we're going to do a few examples of calculations with these different radioisotopes and just different questions about them. So first question says that our radioisotope strontium-90 has a half-life of 38.1 years. If a sample contains 36 milligrams of strontium-90, that's going to be our initial amount. how many milligrams remains after 152.4 years? Okay, so there's going to be two steps that you want to really take to answer this question, right? First, first step, first thing you're going to ask yourself, how many half-lives have passed? In the time period that they gave us, how many half-lives have passed? Okay. And then the second part is going to be to use the half-lives to figure out what's left. Okay. When they give us this half-life value, they're giving us an equality that we can use. They're telling us that every one half-life equals 38.1 years. Okay. So now if we're looking here, they're telling us, well, yeah, but we have 152.4 years that have passed. Well, we can use our equality to figure out how many half-lives that represents, right? We could set up a conversion factor just like we've done for many other things that we've already worked with. Every 38.1 years is one half-life. So if we have 152.4 years, we're going to divide that by 38.1, and that tells us that we have 4 half-lives that have gone by. All right. Once we know how many half-lives we've gone by that have gone by, we can track the decay of our original compound. So if we have 36 milligrams, this is our initial amount. Then at our first half-life, we're going to have 50% of that. So we're going to have 18 milligrams left. Okay. We have to go up to 4 here. So now we're going to have our second half-life. So our 18 milligrams is going to decay down to 9 milligrams. All right. Then we're going to have our third half-life. Our 9 milligrams is going to decay down to 4.5 milligrams. And then finally, we'll be at our fourth half-life. And our 4.5 milligrams is going to decay down to 2.25. Okay. So step 1, we figure out how many half-lives have happened. Step 2, we use the number of half-lives to track how our original compound has decayed. All right. Let's look at the next question. I'll put it up here. I want everyone to see these questions before we solve them out. All right, so this one tells us that carbon-14 was used to determine the age of the Dead Sea Scrolls. If the Dead Sea Scrolls were determined to be 2,000 years old and the half-life of carbon-14 is 5,730 years, what fraction of this half-life has passed? All right, so our scrolls are 2,000 years old. And our half-life is 5,730 years. Okay. So this question's asking us for something a little bit different, but we're still going to use the same reasoning here. They're giving us a time to focus on. They're telling us the scrolls are 2,000 years old. So if the scrolls are 2,000 years old, I can use my half-life equality to figure out how much of the half-life has gone by. Obviously, 2,000 is less than 5,730. So I know I haven't reached a full half-life yet. But I can look at that number and I can say, all right, well, I'm going to take my 2,000 years and divide it by that half-life value, and that'll tell me the what fraction of my half-life has gone by. Okay. So we get 0.35. Okay. That's how much of our half-life we've progressed through, about a third of it. Okay. You can turn that decimal into a percentage by multiplying it by 100. You could say that 35% of the half-life has passed. All right, but we just use our equality to figure this out. Let's look at the next one. Okay, they're telling us that the half-life of the iodine 123 is 13 hours. How much of a 64 milligram sample is left after 26 hours? All right, so they ask us how much of this 64 milligram sample is left after 26 hours goes by. So we still have to ask ourselves that first question. How many half-lives have passed? All right, so we know that 26 hours has gone by. And we know that there's 13 hours in every one half-life. So we know that 2 half-lives have gone by. I know it seems very like a little bit extra to pull all of this out like this, but it's really helpful in not making accidental mistakes. Our second part of this, of answering this question, is going to be to track the half-lives. We're going to track how much of our original sample is getting used up at each half-life. Okay, so we start out with our 64 milligrams. And at our first half-life, we're going to be down by 50% of this. So we're only going to have 32 milligrams left. That's the amount that will be present at our first half-life, but we've gone through 2 half-lives. So at the point where we're at our second half-life, our 32 milligrams will have decayed down to 16 milligrams. Okay. That's why it's important to pull this out into steps and not to just take our 64 and say, oh, it's 2 half-lives. So 64 divided by 2 is 32. Okay. So you're going to end up with the wrong value if you don't go through the steps of like pulling this apart like this. All right. Next question. You're going to see how similar these get. Okay, phosphorus 32, a radioisotope used in the treatment of leukemia, has a half-life of 14.3 days. So 1 half-life equals 14.3 days. If a sample contains 8 milligrams of phosphorus 32, how many milligrams of phosphorus 32 remain after 42.9 days? Okay. So we're starting out with 8 milligrams. We want to know how much is left after 42.9 days pass. So for starters, we're going to figure out how many half-lives have gone by in 42.9 days. We know that there's 14.3 days in every one half-life. Okay, so 3 half-lives are going to go by. Second step, we're going to take our 8 milligrams and we're going to track it down through 3 half-lives. So 8 milligrams down to 4 milligrams, that's going to be half-life 1. 4 milligrams down to 2 milligrams is going to be half-life 2. 2 milligrams down to 1 milligram, that's going to be half-life 3. Okay. All right, let's look at this next one. A lot of words in this one. The bones of humans and animals assimilate carbon until death. Using radiocarbon dating, the number of half-lives of carbon-14 from a bone sample determines the age of the bone. Suppose a sample is obtained from a prehistoric animal and used for radiocarbon dating. We can calculate the age of the bone or the years elapsed since the animal died by using the half-life of carbon-14, which is 5,730 years. All right, so they're saying that we have a bone sample from the skeleton of a prehistoric animal that has 25% of the activity of carbon-14 found in a living animal. How many years ago did the prehistoric animal die? So for this question, the information is given to us in a bit of a different way, but that first question that we need to answer still stands. We need to know how many half-lives have passed. And the information that we're looking at is a little bit different, but we still do the same process. We know that when an animal is alive, it has 100% of its carbon-14 activity. All right. So when an animal is alive, it's got 100% of its carbon-14 activity. Right now, this particular prehistoric bone that we're looking at has 25% of its activity. So it's gone from 100% down to 25%. That's something that we can track using the half-life method. If we start out at 100%, like that's our original amount. So when we go from 100% down to 50%, that means that one half-life has passed. Right? And when we go from 50% down to 25%, which is where our current prehistoric bone is at, that means that 2 half-lives have passed. The other information that they give us in this question is the half-life value of carbon-14. They tell us that every one half-life is 5,730 years. Okay. So we know that each time a half-life passes, this is how many years goes by. So for this first half-life to pass, this was 5,730 years. When this second half-life passes, that's another 5,730 years. So how much time passes overall? We're going to add those two values together. So the bone is going to be 11,460 years old. Or the question was, how many years ago did the prehistoric animal die? So It died 11,460 years ago. Okay. Let's look at one more question that's a little similar to that. This question's giving us the half-life value in terms of fractions instead of percents, but it works the same way. They're telling us that we have a piece of wood that's found in a cave that has 1/8 of its original carbon-14 activity. How many years ago was the wood a part of a living tree? We're still looking at carbon-14 activity here. So the half-life of the carbon-14 is still going to be 5,730 years. Okay. And we're trying to go from our original sample, which has 100% of carbon-14, down to 1/8 of that. Okay. So there's a few ways that you can do this. You can turn 1/8 into a percentage if you'd like. You can literally do 1 divided by 8 times 100. So 1/8 of your original amount would be the same way as saying you have 12.5% left because it's 1 divided by 8 times 100. So if you track the half-lives from 100% down to 12.5%, that's the same way as starting with your original value, your whole value, and tracking it down to 1/8 of that original value. So watch what happens. If you start out with your original amount of carbon-14 in your living sample, we're going to say that that's a whole number 1. Okay. After the first half-life goes by, you're going to have half of that left. So you'll have 1/2 now. When your second half-life goes by, you're going to have a half of this. So a half of a half is going to be a quarter. When your third half-life goes by, you're going to have a half of a quarter, which is 1/8. Okay. So you originally have 100% of your material here. At your first half-life, you've got 50% of your material left. At your second half-life, you have 25% of your material left. And at your third half-life, you have 12.5% of your material left. Okay. In this case, we're looking at carbon-14. So every one of these half-lives that go by is going to be an extra 5,730 years. So this is half-life 1, this is half-life 2, this is half-life 3. So this is 5,730 years plus 5,730 years plus 5,730 years. So that's going to be 17,190 years. That's how long it's been since that piece of wood was part of a living tree. Okay. So for all of these half-life questions, remember that the easiest thing to do is start by figuring out how many half-lives have passed and then using that number of half-lives to figure out either how much time you're looking at or how much material you have left, depending on the question that's being asked. Okay, let's look at the some of the scanner applications for our radioisotopes next. There are a few different applications that are more common than others and some that you want to be able to really focus on. One of the main things with your radioisotopes that are being used medically, again, and we've said this before, but it's worth repeating, radioisotopes that you're using in nuclear medicine need to have very, very short half-lives. What ends up happening is that as the radioisotope is introduced into your body, the cell is going to kind of recognize it as one of its own. So it's going to get incorporated into the cells. The radioactive isotopes are going to be able to be detected by a scanner because they're going to be emitting radiation. And that radiation that's being emitted is what's going to give the image of the organ that we're going to be seeing. And we want the radioisotopes to have very short half-lives so that they decay as soon as possible. So these are just some different types of appropriate radioisotopes that are used medically, and you'll notice that they all have very short half-lives. Different radioisotopes can target different organs more effectively. So you'll notice that some, even on this list, they have some that are for certain things. Okay, like you're not going to use the same radioisotope for every type of diagnosis, every type of scan. After you allow your patient to ingest a radioisotope, that's when the scanner is going to start moving over the organ of interest. And that's when you're going to be able to get the image that you're looking for, depending on the type of detection method used. Okay, there'll be some that are using a photographic plate that are going to be able to detect the radiation that's being emitted from that particular isotope that's kind of like sitting in that organ now, just emitting its radioactivity. So this is an example of the type of scan that is shown from the thyroid when you've had some iodine-131 absorbed. But it's visualization that you wouldn't get otherwise because there'd be nothing in the thyroid to emit something that would interact with the photographic plate. Again, short half-lives. I keep on highlighting it here. Positron emitters that have short half-lives are going to be able to study things like brain function, metabolism, and blood flow. You're going to have these positrons that emit as the decay occurs. And then you're going to be able to detect these positrons. They can be detected by computers, and that's going to allow the creation of these 3D images of different types of organs. So this type of scan is called a PET scan, positron emission tomography. You can actually see the very different brain activity of a healthy brain versus an Alzheimer's brain here. Different areas are being lit up by the positron emitters that have been absorbed. You also have CT scans or computed tomography scans. This is when you have a computer that's monitoring a whole bunch of X-ray beams that are being directed at a particular area. What happens is the scans happen in layers, and you're able to build an image from those layers. So you're going to have differences in absorption based on tissue density and fluids around the area, which gives you a really detailed image of, in this case, the brain. There's also magnetic resonance imaging or MRI imaging. This is an imaging technique that doesn't involve nuclear radiation, and it is considered the least invasive because of that. The MRI imaging is going to be based on the absorption of energy from the protons in the hydrogen atoms being excited by the very strong magnetic field of the MRI instrument. And this is going to give us the visualization that we need because the energy that's absorbed is going to be converted to color images of the body. So you'll be able to see the different energy values as different color, when you're looking at it visually. All right, so these different colors are all representing different energy values in that absorption process. And this learning check is just to reiterate the fact that the radioisotopes that you want to be using for nuclear medicine are the ones with the shortest half-lives possible. So something like the potassium-40 has a half-life of 1.3 billion years. That's not going to be a radioisotope that you'll want to be using for nuclear medicine. Something like potassium 42 with a half-life of 12 hours, or iodine 131 with a half-life of 8 days. These things are much more likely to be used for our radioisotopes for nuclear medicine because they'll be out of the body relatively quickly. There are also different types of nuclear medicine that are kind of being used more often now to like treat different types of cancer. This is an interesting use of that. You have rocket therapy. I never know if I'm saying that right or not, but this is how it's spelled. This is called seed implantation. And this is like an internal kind of radiation therapy. There's two different kinds. There's permanent and temporary, but you end up implanting these seeds of radiation around the area that you have the tumor, the malignant area, you can call it, right? And then you're going to have the radioactive particles in here, iodine 125, palladium 103, or cesium 131. And these are all going to decay over time via gamma emission. Okay. And the radiation that's emitted from that decay process is going to destroy the cancer cells that are around the seeded areas. So they're not going to be able to reproduce and like form more cancer cells. But at the same time, they're not going to do very much damage anyway to the other normal cells that are around them. It's very deadly to the cancer cells without interfering too much with your normal cells. So it's a pretty decent method for trying to fight something that is a very dangerous type of cancer. There's also temporary methods for it, which you can use injections instead of the permanently implanted capsules. The goal would be the same thing, to try to cut off the reproductive ability of the cancerous cells and leaving your normal cells alone. Last thing that we want to talk about for this chapter is going to be nuclear fission and nuclear fusion, what the differences between these two things are. Both of these processes harness a ton of energy. There's only one of these, though, that we're actually currently able to use, practically speaking. The word fission is what it means, splitting something apart into pieces. Okay, so and when you have a nuclear fission reaction, you're going to be taking something with a relatively large nucleus like uranium-235, and you're going to bombard it with something like a neutron, and this is going to make it unstable. Okay, we talked about bombardment before. This is similar to that. That unstable isotope that's formed is going to split into two smaller nuclei that are more stable. But it's also going to produce 3 more neutrons. Okay. And in that process of splitting, when the uranium-236 splits apart into the 2 smaller nuclei and releases the 3 neutrons, it's also going to release a ton of atomic energy. And that energy is what gets harvested in the nuclear reactors. This is what a fission process looks like. So this is going to be your original nucleus, and this is the neutron coming in and bombarding it, and it turns it unstable. And then this is the split that happens. Now you have 2 new nuclei that form, the krypton-91 and the barium-142. You also have formed a ton of energy, and you've released 3 neutrons. That's what happens as a result of fission. These neutrons then, they go find their own uranium-235s, and the process continues on. All right, so this type of process that is self-perpetuating is called a chain reaction. It means that when this first nucleus splits and it forms 3 neutrons, that those 3 neutrons are going to go find their own uranium-235s. And then those 3 new uranium nuclei are also going to split. And each time they split, 3 more neutrons are released for each one. And now each of these are going to go find their own uranium-235, and they're going to impact it, and they're going to split that uranium-235. And that process keeps going and keeps going. And every time you have a split, you have this creation of energy that occurs as well. Okay. Fusion reactions are the opposite of fission reactions, because instead of taking something that's large and splitting it up um, into smaller pieces, you're going to be taking two smaller nuclei and combining them into larger ones. Okay. Just like fission, nuclear fusion also releases a lot of energy, a large, large amount of energy. This is the type of process that's occurring continuously on the sun and in stars. Um, these fusion reactions happen at just staggeringly high temperatures, temperatures that are so high that we are unable to harness any type of fusion process for use, like on Earth. We don't have anything capable of housing a fusion reaction. The only type of nuclear reaction that we're currently able to actually use is the fission reactions for that reason. This is an example of a fusion reaction. Here we have two hydrogen nuclei that are combining, and they're creating a larger helium nucleus. They're also releasing a neutron and some energy. Okay, so we have things that are joining together to make a new nucleus. That's an example of fusion. Right? So if we want to look at some of the differences between these, we just want to be able to read each of these statements and indicate whether it's fission description or a fusion description or both. When we have a nucleus that splits, that word right there, let's get our pen out. When we see that word split, we're going to immediately associate that with fission. Okay. This one says large amounts of energy are released. This is going to be true for both fission and fusion. Okay, so both of these. Smaller nuclei form larger nuclei. Let's switch colors for this. So we have small nuclei forming larger ones. So we're taking two things that are smaller and combining them to form something that's bigger. That is going to be fusion. We have hydrogen nuclei reacting. Hydrogen nuclei are very, very small. And when you have your hydrogen nuclei reacting to form something bigger, again, that's going to be fusion. Several neutrons are released. We know that when we have fission reactions occurring, we see multiple neutrons being released as a product of that. Okay. So nucleus splits, fission. Large amounts of energy released, both things. Small nuclei form larger nuclei, fusion. Hydrogen nuclei react, fusion. Several neutrons are released, fission. Okay. Sorry. All right. Let's look at this equation. And this one says supply the missing atomic symbol to complete the equation for the following nuclear fission reaction. And here, this is just like any other nuclear equation that you work with. We're going to write down the particles that they're giving us, and we are going to find the missing piece. Take a second to write this down and try it out. Even if you tried it in class, just take a blank piece of paper out and try it again now. Okay. We want everything balanced on both sides of the equation. right? One thing that's trickier on the product side that you want to be mindful of is that they're telling us that we have two neutrons here. So we don't just have one and a zero here. We've got two neutrons. So that's kind of like writing plus this, right? We've got two of these neutrons plus energy. I ran out of room, sorry. So the way that they gave it to us was 210N. But when we want to write it out for our equation, we should write it out individually so that we don't forget it in our overall count. Now what's up here? We have 236 total. Down here, we have 92 total. Okay, so now when we look up at our mass numbers up top, we have, I'm going to do 236 minus 137 minus 1 minus 1. So we're going to have a mass number of 97 total for our missing radioisotope. And now for our atomic number, we have 92. We're going to subtract 52. These are zeros, so they're not going to affect us. So we have a 40. And then we look at 40 on our periodic table, and we see that it's ZR, zirconium. That's our missing particle. Okay, but it's the same exact thing that we did with our earlier nuclear equations. All right, let's look at one more question here. This is asking us to look at these two reactions and differentiate them, fission versus fusion. And just remember that like fusion is combining and fission is splitting apart. Okay. So here we've got these two helium isotopes that are combining into a larger helium isotope. And then additionally some hydrogen atoms or some protons rather. But we have these two helium atoms combining into one larger one. So that combination of two things into one thing, that's what's going to make this fusion. Okay. Over here, we've got a neutron colliding with uranium-235, and then that uranium-235 splits into two things. Okay, so that's a split that's happening. Whenever we have one thing that's larger splitting into things that are smaller, that is going to be fission. Okay. So hopefully that all makes sense. That's chapter 5, though.